So in example 9 here, we have not a can of a Minute Maid fruit punch, but a can of R&R soda. Ooh, yummy, yummy, yummy. I don't think they make that anymore in the cartoon world. But it says a cylindrical aluminum soda can or a Minute Maid fruit punch can is designed to hold, soda can is to hold 12 ounces of a tasty beverage. All right. What are the dimensions of the can that will minimize the amount of aluminum used? So back in the day when someone came up with tasty beverages, they thought it would be nice to offer that tasty beverage to other people and to make it portable. So they had to come up with, first of all, what amount of soda is reasonable to expect one person to drink in one sitting. And I'm sure that had a lot of experiments that went into coming up with 12 ounces, right? Then they had to decide what shape to make the container for those 12 ounces. And I'm sure they came up with all different types of shapes, right? Like rhomboids and maybe cones or something, maybe octagonal polyhedra or something. But anyway, the cylinder was decided upon. And then they had to decide on the material to make that aluminum can out of. Sand didn't work so well. Neither did glass. So they went with aluminum because it's malleable and it's plentiful and relatively inexpensive. But then they had to decide, okay, now that we know that our little cylinder is going to be used to hold 12 ounces of beverage, do we want to make tall cylinders that are really narrow? Or do we want to make, really, really short cylinders that are like this? Now, if it were something like this, here's the drink hole right there. Someone spoke up and said, that one's not going to fit in the Coke machines. And the people at the meeting said, what's a Coke machine? Because the can preceded the machine. But someone pointed out that even though that might hold 12 ounces, it's going to be really hard to hold, right? You have to use both hands and kind of like, and tilt it in, right? So this was probably decided against just out of hand. That's no good. The tall, skinny one could be viable, but when you grab it to drink, your fingers wrap around and touch each other. Ugh, that's kind of gross. You ever done that? You ever reached around and have your fingers touch? Ugh. So that was creepy. This was the creepy design. But what they did is they turned it over to the engineers. They turned it over to the engineers and they said, you know what? I think this idea is going to take off. I think we're going to be selling a lot of these things. So in the interest of being human, we want to maximize our profits. And to maximize profits, we have to distribute this with as little material as possible because that increases our profit margin. So the engineers say, okay, we can do that. And they go back to their math labs and they sit down and they come up with the optimal dimensions for such a can. All right, so here's the can over here. I'm going to draw another one over here. Just a generic cylinder. The important dimensions are the radius of the top, because that's an indicator of the size of the circle. And, of course, the radius of the can. And the other relevant dimension is the height of the can. Those are the two important dimensions for a right circular cylinder. We are trying to minimize the amount of material that we're going to use. So that translates to what quantity? Not volume, surface area. Good. We're trying to minimize the surface area. All right, so let's go ahead and come up with the primary equation for the surface area. Now, the surface area of a can is going to be twofold. You're going to have the circular top, and there's another one on the bottom. So we'll call it A for area. There's two circles, right? So I'm going to have 2 times, what's the area of one of the circles? Pi r squared. So it's 2 pi r squared. That takes care of the top and bottom. Plus, we have what's called the lateral surface area. And if you were to take one of those cans and kind of with your parents' permission and help, cut it open like that, cut it down the side, and then lay it flat, it's going to look a lot like a rectangle. Good. Okay. And the height, the height will be h. No. You just spoke up before I finished the question, so I went to you for the answer. What would be the length of this rectangle? The circumference, right? The circumference, which is 2 pi r. All right, so if you multiply 2 pi r times h, you get the lateral surface area. We'll put that over here then, 2 pi r h. All right, so there's the equation that we're trying to minimize. Right now it's in terms of both r and h. That's not good. We want it to be in terms of either r or h. So what's the constraint? Well, it has to hold 12 fluid ounces. 12 fluid ounces does not work well when you have units of inches. But we can measure volume not by fluid ounces, but by space. So it turns out that 12 fluid ounces would occupy 21.6562 cubic inches of material. Okay? So that is our constraint. So I'm going to come over here and say 21.6562 inches cubed is going to equal the what of this can? Volume, right? And volume is, of a right circular cylinder, it's the area of the top, which is pi r squared, times the distance between the top and bottom, which is h. So pi r squared h. That's the formula for the volume of a, I'll just put it here, of a right circular cylinder. Okay, so here's our constraint equation. You want to solve that for r squared, or h? Definitely h, right? Because there's only one h to substitute in over here, and h ends up being the easier one to solve for anyway. So we know that the height is 21.6562 divided by pi r squared. There we go. I'm actually going to box that one because I think I'm going to come back to that. You'll need a calculator for most of these calculations, so if you happen to have one, that's great. I'm not going to use the calculator on the computer. I'll just type it in over here. All right, so for now, I'm plugging that in over here into my primary equation to get an equation in one variable. So I know that the surface area A is 2 pi r squared plus 2 pi r times this quantity, which is 21, again, 0.6562 all over pi r squared. And since I have that now in terms of a single variable, let's go ahead and come up with a reasonable number for r. Can r be 0? No. What would the can look like if r were 0? Yeah, it wouldn't be. It would just be like a rod of aluminum, right? It's like, how do you get the soda out of there? I don't know. How do you get it in there? I guess it's a non-problem problem. Could it be negative? No. So we know that r has to be greater than 0. And there probably is some reasonable upper bound, you know, that's less than 1,000,000. But it's not super important, okay? So now we will clean it up so that we can take the derivative a little bit more easily. So 2 pi r squared, there's the first one. And in that second term now, this pi divides out with that pi. And this r divides out with one of those r's. So we're left with 2 times 21.6562. I'll just leave it like that. And then it's divided by r, which is r to the negative first. Okay, I wrote it like that so that I could take the derivative of it. All right, here we go. A prime of r, or just a prime, or dA dr, whatever you want to call it. That's 4 pi r to the first minus 2 times 21.6562 times r to the negative second. All right, let's go ahead and factor out least powers. We want to get this into a single term. So if you want to put it r squared in the bottom and get a common denominator, that's fine. I think I'm just going to factor out least powers. I'm going to pull out a 2r to the negative second. Are you okay with that? And that's going to leave me a 2 pi r what? Well, it's 1 minus negative 2? 3. So 2 pi r cubed minus the 21.6562. And so if I write this now in one final cleaned up version, I have 2 times 2 pi r cubed minus 21.6562 all over r squared. So So there's a nice cleaned up version of a prime. Well, we want to know now where a prime is equal to 0. And so that's going to be when the numerator is equal to 0, right? Which the 2 doesn't even really matter. So it's going to be when 2 pi r cubed minus that equals 0, which is when 2 pi r cubed is going to equal 21.6562. So notice I saved a couple of steps there. I already divided both sides by 2 to get rid of it. And then since that minus that was equal to 0, I brought the 21 across and made it positive. And I'm going to wait to pick up my calculator till the very end. So r cubed is going to be 21.6562 divided by the quantity 2 pi, and then I'll take the cube root of both sides. So we get the optimal radius to be the cube root of 21.6562 all over 2 pi. Now, we could do a modified first derivative test for a global argument and even do a modified second derivative test, which that might be a little bit easier, okay? Since there's so much at stake here, I would hate to think this is the one that minimized it and it actually maximized it, and now I'm costing the company a lot of money. So let's just real quickly check. And I like the second derivative here than the first, because remember, the second derivative doesn't require plugging in numbers on either side. I'm going to take the derivative of that version. So over here where I have room, a double prime, that's going to be 4 pi. And then it'll be plus 4 times 21.6562 r to the negative third, which puts it over r cubed. All right, now notice that for certain values of r that are negative, that's going to make the second term negative. And then depending on the size of that negative number, 4 pi minus the number could be positive or it could be negative. It's exactly what I'm getting at, yes. We don't have to worry about all that, right? Because we said that r has to be positive. So this makes it a lot easier. If r is a positive number, we have a positive number plus a positive number divided by a positive number. What do we know? We know it's positive. So here's what we kind of did on the quiz. A double prime is greater than 0 for all r greater than 0. Now again, if you're forgetting what that means in terms of extrema, positive second derivative, you have plus signs in your eyes, you're happy, you're smiling, right? And so now you could say, so r equals, what do we end up? The cube root of, the cube root of 21.6562 all over 2 pi inches minimizes, I'll put in here, comma, absolutely, you don't have to do that, minimizes the surface area. Okay, and again, it's a global argument because we're saying for every single value in our relevant domain, the graph is concave up, and therefore it's not just a local min, it's an absolute min. All right, so we know we have the right value. So now we want to answer the question. Ultimately, if we're the engineers on this team, we're going to have to turn over the dimensions of the can to production, right? But not before design gets a hold of it, all right? We're just engineers. So if the dimensions say, okay, blah, 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 what are the dimensions? So let's go ahead and find the radius and the height. Those are the two important ones. Or actually, let's do this. Let's find the diameter. Let's find the diameter and the height of this can. Okay, kind of the overall dimensions. All right, so the diameter is pretty easy to find, right? The diameter is going to be 2 times the cube root of 21.6562 all over 2 pi. Now here's where I'm going to pick up the calculator for the first time, and I want to get that number. So I'm going to do it kind of in several steps, and then I'm going to store it. I'm going to do 21.6562 divided by. Now when you divide by 2 pi, you got to be careful. If you don't put 2 pi in parentheses, you're going to divide by 2 and multiply by pi. So you either divide by 2 and then divide by pi, you use the horizontal division bar, or you put the 2 pi in parentheses. Then I'm going to take the cube root of that, so I'm going to raise that to the 1/3 power, and then I'm going to double that. So it turns out that the optimal diameter is 3.021093205 inches. We want to go more than 3 decimals here because money's at stake, right? We want it to be as optimally possible. And now I'm going to store that on my calculator. I'm going to store that as A. All right, sweet. So now I know the diameter. Let's go ahead and find the height. The height, remember, should be, hey, there it is. Remember that? We boxed it, so it'll make it easy to find. It's going to be 21.6562 all over pi r squared. All right, so that's going to be 21.6562 all over pi times the diameter divided by 2 squared. Because I stored my diameter, I just got to be careful, right? And let's see what that comes out to be. So I'll do 21.6562. I'll divide it by pi, and then I'll divide it by my radius, which is alpha A divided by 2, and I'll square that. So if you're doing these with me, that's awesome. You could verify my calculations, or you can trust me. It comes out to be the following number: 3.021093205 inches. All right, so there we are. Our work as engineers is complete. All right, so now we go back to our boss and we say, the optimal can that holds 12 fluid ounces would fit perfectly inside of a cube. That's 3.021093205 by 3.021093205 by 3.021093225. Right? Got it? What do you know? The diameter of the optimal can and the height of the optimal can are the same. Say it. Square, square, square. Nature loves a square. Nature loves a cube. In 3 dimensions, the cube is the square, right? So is that now, when you turn it over to design, is that how the cans are actually made? This is a pretty typical 12-ounce can. So anything that is not a perfectly 3-inch tall by 3-inch wide can is going to be costing the company more money. All right? So why then is the can not 3 inches wide essentially by 3 inches tall? Yeah, there's lots of reasons. It actually turns out to be, and you can measure this one if you want, it's actually 2.6 inches in diameter, and it's about 4.75 tall. So let's kind of draw the other one next to it. The actual one is 2.6 inches, and what did I say, I pre-measured 4.75. All right, so you said it's hard to hold, right? And we've already kind of talked about that in the extreme case. There are studies where, you sign up to be part of a study, and the study involves this. Here, hold that. Okay, give it back. All right, write down from 1 to 10 how that felt. And then I'll hand you another one that's a different diameter. Hold that. And you write down how you feel. Hold this. Write down how it feels. So the ones where it's too narrow, like the Red Bull cans, people touched it and their fingers touched it and they went, ooh! Is there a category for ooh on 0 through 10? Like -10. Ooh, creepy. And then there was the one where, they give them too wide and you try to grab it. And before you even grab it, your hand starts cramping. That's painful. All right? So really, you hand it over to design, which doesn't care about optimal anything, right? There's no price we won't pay to make it look cool. All right? So somebody decided that 2.6 diameter was comfortable for the average person more so than 3 inches. Okay, so there's the first thing. If they're going to be making it a little bit more narrow than usual, they're going to have to make up for it where? In the height. But does that seem like it's a 1-to-1 trade-off? We made it 4/10 of an inch narrower, and we made it 1 3/4 inches taller. Yeah, there are a lot of other things involved. Very good. First of all, there's 12 inches of soda in here, supposedly, but what's at the very top of the can? There's air in there. There's a little bit of air in there for pressurization. Also, if you look on the bottom, it's concave in towards the fluid in there. Why is that there? Well, this little concave thing on the bottom is actually to help increase the pressure on the inside. It's like pre-stressed in there. So it helps maintain the pressure. So if you're going to be cheating from the bottom to make this concave thing, and you're not allowed to change the width, because that's the comfortable one, remember, then you're going to have to make up for it in height. So the first cans were actually just cans like this. Like if you've ever opened a can of green beans from the pantry, taken the lid off, and then try to drink the green bean juice. I love that. That's how the first cans were. They were just literally cylinders. And then they used like lead solder to put the lids on, and everyone was getting lead poisoning when they were drinking their green beans, or RC Colas or Pepsi Colas. Well, that changed now. So they now have this little tapered edge all the way around the top and the bottom. So that's a relatively new design. Why is that there? Yeah, it serves a couple of purposes. When they stack these, one inside the other, the ring at the top is designed to fit so they don't slide. That's good. Okay? And the other thing is ergonomics. If you've ever drinking the green bean juice, or maybe the pineapple juice, right? When you put the can on your lip, you're like, oh man, I love green bean juice, but this just doesn't feel right, right? This right here, this little piece at the top, that is ergonomically designed to hold your bottom lip. Oh, that's so comfortable. I don't even need to sip. I'm just going to hold it right there. Oh, it's so comfortable, right? It makes drinking so much more pleasurable. So, in other words, you're cheating all over the place to make this can more streamlined, more ergonomically friendly. And if you're not allowed to adjust the width, the only place you can make up for it is in height. Yeah. Now, the optimal can is about 3 by 3, and those cans do exist, right? We started buying them for my daughter because she was not in on the original study where they decided that 12 fluid ounces was what the average person could drink at one time, because she just left her half-drank soda cans all over the house. So anyway, we started buying the little short guys. Have you seen the short ones? They're about half this tall. They're just as wide, the same width, but they're half as tall. Those are more towards the optimal size, but they only hold 8 ounces instead of 12. So interestingly enough, it is worth the extra money to produce a can that is not purely optimal because it looks cool, it's more stable, it stacks easier, ergonomically people are more happy with it. Now there are some companies that have 12 fluid ounces, or any ounces for that matter, that deliberately exaggerate well beyond just cheating a little bit here and there. They spend a lot more money on their can. Why? Well, the first example that comes to my mind is when you turn 21, you'll hear this thing called beer. Beer comes in both cans and bottles. But if you look at the cans, if you stacked up the average beer can on the table, they'll all be about 4.75 high, except one that is a little bit narrower and therefore a little bit taller. It's the Silver Bullet. Well, Michelob Ultra is also. Thank you for being so knowledgeable about a subject I didn't even think you knew existed. Michelob Ultra is a little thinner and a little taller, and so is Coors Light. They're a little bit thinner and a little bit taller. Michelob Ultra is actually thinner than Coors Light. So why would a company then deliberately spend more money on a taller but narrower can? Not like creepy narrow, like, ooh, my fingers are touching like Red Bull. What's that? To be unique, right? Product differentiation. They want to be unique. And there's also some very shallow-minded people that see a taller can and they think, more beer! Right? Power means more. Give me that one. Right? They're catering to that market too. All right? So there's a lot of design that goes into the can. But you know what? It all started with the calculations in the engineering laboratory to come up with the optimal dimensions, and then they deviated from there. Okay? So that's cool. That's cool. Any questions about that? Of course, then the Coke machines were designed to take the cans, okay? So what came first, the Coke machine or the Coke can? The Coke can did, right? All right. Let's shift gears here a little bit then. Example 10. We have time. The manager of an 80-unit apartment complex. Maybe you could make yourself the manager. It's always fun to put yourself into the problems. So congratulations. You are all now the manager of an 80-unit apartment complex. And you are trying to decide, because it's part of your job description, what rent to charge. Okay? The owners have put you in charge of deciding what the rent is. Wow, that's a big task, guys. You have records from the past. Experience has shown that at a rent of $200, we'll say per month, all of the units are going to be full. Well, heck yeah, $200 a month? That's downright cheap. Of course, you don't know when this problem was written. This could have been written during the Dust Bowl era, right? But anyway, at $200 a unit, all the units are going to be full. On average, one additional unit is going to remain vacant, unoccupied, for every $20 increase in rent. Find the rent that we need to charge, or you need to charge, so as to maximize revenue. To maximize revenue. Counterintuitive, though. It might be that we get more money by having some of the apartments unoccupied. That would also cut down on the customer complaints, right? So maybe if we leave them all vacant, then we'll have no complaints. And we'll have no job either. Okay, so let's go ahead and just start establishing what is the profit at certain times. Let's let this column be N. And let's let N be the number of price increases. The number of price increases. That's kind of important. All right, so with 0 price increases, what's our profit? Our profit is going to be, well, let's see. We have 80 units at what price per unit? 200, right? So we're going to have 80 times $200 per month. I don't even know what that is. I don't have a calculator. It doesn't matter. When you are trying to find a pattern, you almost don't want to multiply it out, because when you look at a single number, the pattern is already absorbed into that. So I'm just going to leave it as 80 times 200. All right, let's go ahead and raise the rent one time. But we're going to do it on paper. We don't want to raise the rent and anger a bunch of tenants if we don't have to. So maybe this is going to be our biggest profit. Who knows? Let's raise it once on paper. If I raise it once, how many units are now going to be occupied? 79, also known as 80 minus 1. Times, what's the price now if I raise it one time? Yeah, 220, or also known as 200 plus 20. Let's raise it again. Now, how many units are going to be occupied? Yeah, 78, or 80 minus 2 is better. And the new price is 200 plus 40, or 2 times 20. How about that? Let's raise it a third time. Now we're going to have 80 minus 3 units occupied. And each of them are going to bring in 200 plus now 3 times 20 apiece. And I think at this point, you probably can see a pattern emerging. What you're trying to do is let that number, the number of price increases, be visible in your calculations so that you can say it in general. All right, so let's go for it. The profit as a function of N. I'll use P for profit. We've already defined N as the number of increases. It's going to be, what? 80 minus N times 200 plus N times 20, or 20N. Good. So notice by writing it this way, we already have one equation with one unknown. We've already got the constraints taken into account. The fact that as one goes up, the other goes down. All right? So now what we're trying to do is just do what with that equation? We want to maximize it. All right, now what's a reasonable N? Well, N can be between 0 and some upper bound, right? If I raise it enough times, I'll have a rent so expensive, no one's going to want to rent there. So whatever that upper bound is, that's fine. We just know N has to be greater than 0. Could it be that you have a negative value of N? No. A negative n would mean that you lower the rent $20, which might be viable if what? They weren't already all full. If they weren't already all full, then you might want to try to lower the cost. But we're already full, so we're just going to raise it. All right, let's go ahead and find the derivative.
We are no longer doing the announcements on the TV. If you guys would please, teachers, please check your emails for the announcements, and then please subscribe to that channel so you get updates on it for announcements. And
I'm using the product rule here. Product rule, okay? Derivative of the first times the second plus the first one times the derivative of the second. All right, now I want to know where that thing is equal to 0. So from here, you can perhaps distribute. We got negative 200 minus 20n plus 80 times 20, that's going to be 1,600 minus 20n equals 0. So we end up with negative 40n, and then this becomes plus 1,400. Let me just go ahead and bring that across. That'll be equals negative 1,400. And if I divide through by negative 40, we get positive 1,400 now, divided by positive 40, because negative over negative is positive. The trailing zeros divide out. Those are both even. 4 goes into 14 without going over 3 times. With 2 left over, 4 goes into 25 times. So there it is. N equals 35. Now, is that going to be a max, the value, the number of increases that maximizes or minimizes? We can check, can't we? All we have to do is find the second derivative and look to see, and the graph should be concave what if this maximizes it? Should be concave down for all n greater than 0. It is. I'm going to let you verify that on your own because we're kind of running out of time. But 35, and you got to be careful here. You don't want to be that dumb manager that says, I knows how to do calculus, but I don't know how to interpret my number. And now it says here, I got to charge everybody $35 a month. Ooh, way to get yourself fired as a manager, right? This is the number of price increases. So now if we want to figure out the profit, we can plug it back into P of N. If we want to figure out how many units are going to be occupied or unoccupied, we can plug it into 80 minus N. If we want to figure out what the new rent to charge is, we can plug it into 200 plus 20N. What did it ask us? Find the rent to charge. Okay, so the optimal rent is going to be 200 plus 20 times 35, which let's go ahead and figure out what that's going to be. 20 times 35 is 700. Oh boy, that's $900. Send out that memo to all your tenants. Due to calculus, we are now raising your monthly rent from $200 to $900. Have a good life. We hope you stay, right? So $900. Now let's see, based upon that rule, how many are going to be occupied. The number of apartments occupied now is going to be 80 minus 35. So 35 people have checked out, which leaves what? 45 tenants. We have 45 tenants. Wait, that's tenants like belief tenants. This one is tenants like apartment dwelling people. All right, and then you can figure out, of course, what the maximum profit is. You could do 45 times 900. Now, here's what's interesting. To maximize your profit, charge $900 a unit, and 35 of them are going to be vacant. 35 of them are going to be vacant. Which then you do what? You rent out those 35 on the down low and charge about $850 a month. So that, you know what I mean? But don't let the other 35 people or the other 45 people that are paying $900 find out that you're offering a lesser amount to those other people, right? Otherwise, you'll have like people problems on your hands, and you don't want that. Anyway, there you go. So kind of counterintuitive. You're maximizing your profit when you're not filled to capacity. And that might happen in the real world. All right, so for a problem like this, again, it wasn't a geometric problem. We didn't really have constraints. We just had a single variable. We looked for a pattern. We came up with our equation, and then we just found the absolute maximum of it. All right, we'll stop right there for the week. We should be able to finish up the optimization notes rather easily the Monday we get back, which is the 27th. So it looks like Tuesday the 28th is when your worksheet's going to be due. Don't let this one sneak up on you. And we'll have another quiz on that Tuesday, okay? Have a fantastic Turkey Day and holiday.